Right, so what we're looking at now is, if we're looking at the next topic, which is topic number 2, and we're looking at the components, and that's the main word here, of work and force. Now, if we look at, remember example 4 from the previous video, the one with the waiter, right? And what we understood about the waiter is that the waiter was moving across, but at the same time he was holding his tray. So he was moving this tray over here across the room, but he was holding it in his hand and above his head. So what happens here, it creates this angle here in between our force, our displacement and our force. So if the conditions here are, if the force acts at an angle theta to the horizontal. Right, so the conditions for that is something like this. So suppose I had, so if I look here and I say, suppose I had, we have a force acting at an angle, acting at theta, which causes the object to move horizontally. Right, so it's moving horizontally and it covers the displacement. And let's say that's delta x there. Alright, so if I had to look at it, I have, let's say, this situation. Let's say, for example, I have a pulling force here. I'll do another color so we can have a look. I have a pulling force here, right? This force, it means that I've got a force applied. And let's say, for example, we're pulling and our applied force is at this angle theta here. And I want to move this whole thing. So just make a note, it moves to the right. So the motion here, or the displacement rather, right? So it moves, it displaces itself. The displacement is horizontal. Right, so if I'm looking at this kind of a setup, I've got my force applied that's moving northeast. If I look at my cardinal points, so there's my force applied, but my displacement is now moving east. So my displacement looks something like this. All right, so I'm starting off at position 1 and it moves to position 2. If I have that situation, then if that's the case, then therefore no work can be done. Right? Now, I know that work is being done because there is force and there is displacement. The fact that the force and the displacement are not in the same direction is a problem. So what we need to look at is how to calculate work done. How to calculate work done. So in the above situation, the work is not done by the force because the force and the displacement are not in the same direction. Please make sure you're taking down all the notes, you're taking down all the diagrams and so on for these types of questions so that you have a better base to study from. Alright, so we can see that because of that delta x and it's moving left to right, you need force. So the fact that I have a force and the fact that I have some sort of displacement, then I know that it's possible to have work done. Right? It is a possibility. So now we need to show how does that work take place. So I know that if I have a force and it acts on an object and the object is displaced an x amount along the surface, that the force x at an angle and the force x at an angle at theta to the displacement of the object, I need to understand that the direction will determine the angle theta. Right, so what we need to actually do is we need to solve this force into the components. So let's have a look. Right, so if we look here, I understand that if I have an object and it's being pulled at the force, this force, the force applied is actually equal to F res from grade 11 now. And that means that that force applied can be divided into its components. So now I have components. So remember your vertical component, your Fy, your formula is F sine theta. And for the Fx, it's Fx, F cos theta. Right? In this situation, let's just look at the two things. If I'm looking at the vertical component, my lifted up one, which is my Fy, then I know that work is being done is equal to force times displacement, right? I also know that I've got work would be equal to this force, which is Fy. So I'll have F sine theta times delta x. And that gives me W is equal to F delta x sine theta. So that's if my object was moving in a vertical way, it was being lifted up. But in the scenarios we're going to be working with, we're going to look at horizontal forces, so to move across the surface. So that's our main thing now, to move across the surface. This is where we're at. So I can have W is equal to F cos theta, delta x, and W is equal to F cos theta times delta x. And that gives rise to a formula that says W is equal to the force multiplied by delta x multiplied by cos theta. So remember I said earlier in the first video, I said that it's not correct for us to use the formula for work done is equal to the force times the displacement. That is a not acceptable formula, because that means we can only use that in conditions where the force is actually in the same direction as the displacement, but where our situations are not going to be aligned in such a way. So what I want you to do is, this is our main formula we'll be using, highlighted and so on, and let's just have a look here at what everything means. Right, W over here, W here is the work done by a force on an object, and that can be either measured in joules or Newton meters. Right. F here is your magnitude of the force, and it can be an applied force, frictional force, so applied force, force of friction, spring force, tension force, whatever the case is, acting on the object, even tension, and that's measured in newtons. Your delta x here is your displacement, right? The displacement is measured in meters, and then we have our theta here, which is the angle. This is important. Please make a note for yourself here. It is the angle between the force, which is F, and the displacement. Which is delta x. Right? So this is important, that theta value over there. Now let's have a look at the conditions for theta. So let's have the first one. Condition A. If the force is moving in this direction and your displacement is also moving in this direction, then theta will be equal to 0 degrees. Right? Therefore, when you substitute it in, you're going to substitute in cos theta is actually going to be equal to cos 0, and that actually gives you a positive 1, right, from math. So therefore, work done is equal to the force times delta x cos theta, and you will substitute in 1 times 1 times cos 0 degrees, and that will give you 1 times 1 times 1, and that's going to give you 1 joule. So work is equal to 1 joule, and that value, your work done, right, work done is greater than 0 joules. That's important. That's your one condition. So if the forces are equal, the force and the direction are in the same direction, then you should have your work done being greater than 0. Right, the second condition you look at, condition B. Condition B is if the force is going in this direction, but the displacement is moving in the opposite direction, then you have a situation where your theta value is equal to 180 degrees. So therefore, if I'm going to have cos theta is equal to cos 180 degrees, I'm actually going to get negative 1. So I can say that W is equal to F delta X cos theta, which is equal to 1 times cos 180 degrees, which is equal to 1 times negative 1, which then gives me negative 1 joules. Right, when I have this, my work done is less than 0 joules. Right, now this tells me some sort of information. When I'm looking at the amount of work being done, work done is my energy usage, right? Or how much energy I'm contributing to the system here. So when I'm looking at this situation, situation B, this is when I have things like friction, or I have things like air resistance. Those things all oppose motion each time. So I could have my force going in one direction, but my object moving in the opposite direction. Then I'm going to have work done less than 0 joules. But we're going to look at in a bit what that actually means. All right, the next thing is condition C. And in condition C, your force is, let's say, in this direction, but your displacement is at 90 degrees. So your theta value is equal to 90 degrees. And I know that if I have cos theta and I say cos 90, I know that cos 90 is 0. So therefore, that means if I had work being done, work is equal to force times displacement, cos theta, and I've got 1 times cos 90. I'm going to end up with 1 times 1 times 0, and that's going to give me W is equal to 0 joules. So if I have my force going in an upward direction and 90 degrees to my force, perpendicular to my force, I have my displacement, then I can say no work is done, or work done is equal to 0 joules. And that's my third condition for theta. So I have these three conditions, and everything is governed by those conditions. If I have forces that are going in the same direction and they contribute to the direction of my object, then I've got what I can call positive work done. If I've got a force going forward and I've got friction or air resistance, I can say that I've got negative work done. And if I have my force and my object's displacement at 90 degrees, if I say they're at perpendicular to each other, then I can say that no work is being done for those. At free body diagrams, just want to go through these different free body diagrams so that once and for all you have these forces, these free body diagrams sorted out. So the first thing we have here is that they need to be drawn with a pencil and a ruler. All forces need to be represented by arrows pointing in the direction of those forces, and do not ever draw force diagrams. Now what we mean by force diagrams is the one with the block. We're going to only do diagrams that use a dot as an object. So let's look at the first scenario. The first scenario is that if you have a stationary object on a horizontal surface, it's not moving. So I draw in my dot because it has mass, and please you use a ruler when you do these. It's going to have some sort of Fg or mg or weight. And then going upwards, I've got force of the normal. So if it's stationary, there are no horizontal forces like force of friction or force applied. In these situations, your force applied can be equal to your force of friction. So in these situations, we have equilibrium. Right, the next one is an object moves across a horizontal surface. The fact that we're saying it moves means it's in motion. And let's say the surface here was a surface with friction. Right. So I have my dot. It has mass. So I've got some sort of mg here. Up to the top, force of the normal. I know it's moving and it's being pushed towards the right. So I've got a force applied there. And I know that it has some sort of friction. And because it's moving, my line for force of friction is much smaller than my line for force applied. If there was no friction and it was a frictionless surface, then I would have a situation where I don't have the red force, that's frictional force. I can leave that out. Right, let's have a look at object or scenario number 3. Right, for scenario number 3, there are two ways you can draw it. We can either draw the net force free body diagram, or we can have a component. Right, I'm going to do it without friction, and then I'll show you how we add in the frictional forces. So when I work with net forces, I need to look at all net forces that are applied on this object. So net force diagrams for me are not the most don't provide us with the most amount of information, mostly because they just lack giving us information of the things we do need. Right, so let's have a look. I've got mass, so I've got to definitely have my Fg or my mg, and then I've got my force of the normal there. Now for F net, because I'm showing net forces, my force applied, I must show this, is up here. And over here, I must show my angle theta. And that will be force applied. Right, so you have to show this. Now I know that force applied is at an, let's have a look here. It's at an angle theta, so I can solve it into its components rather. And what I would be left with is still going down this way, I've got my mg or my Fg. Going up this way, I've got my normal force. Going towards the right, I've got my Fx, my F horizontal. Going upwards, that's accompanying that normal force, is my Fy. And I cannot have my F net, which is at an angle. Now, if I wanted to have friction, then I show friction is always towards the motion. So this object, I know that this object here is going to move across the floor. So friction will have to be in the opposite direction to that motion across the floor. So for both diagrams, I'll draw force of friction there, or force of friction is drawn there. And that's my frictional force. You can either draw the net force diagram or the component diagram, but you cannot mix the two. For example, I cannot have an angle coming through here and call that F applied, while still having the F and the Fx and the Fy there. This here, you're not allowed to do on a component diagram. So you either draw the net force or the component, but never both. Right, let's have a look here for objects on an incline. Objects on an incline, you can also draw the net force diagram, or you can draw the component diagram, but never a combination of the two. So I've got this object here, and it says it slides, which means the only force that's really acting on it is Fmg or Fg. Alright, so let's have a look here. For the net force, I know that I have Fg, and my incline is here. I'm just drawing a dotted line to show you. So I've got force of the normal there. Now, that's the only thing acting on the object. If the object had some sort of friction, so even though I know that this object's natural motion is to slide down, it's a natural motion brought about, by gravity. So it's not something that I can't show force applied, but I can show that if the natural force, the natural motion is down the slope, then the force of friction is in the opposite direction. And that's how I would draw my force of friction. If I do a component free body diagram, I've got my surface there. Going up from my surface, I have my normal force. Going down the incline, I've got my F parallel, which is mg sine theta. Going in line with the force of the normal, I've got my Fg perpendicular, which is mg cos theta. Then because if I'm looking at the situation, if this is the only thing, it just slides down the hill, then I've just got that mg sine theta which assists it. If I had friction, then friction would go up the slope. Right, so against that natural motion. So when we talk about the natural motion, we're talking about We're talking about things like F parallel, mg sine theta, which is going to bring the block down. What we're not allowed to do then is, if I'm drawing this component free body diagram, then I can't have this force of gravity coming down here. That's not allowed. I also, in the other situation, I cannot put in here force applied, because you're not applying any force. It's just sliding down. So that's also not allowed for each one of those, but we've discussed that previously. Right, situation number 5. It says here that an object is being pushed up an incline. So I've got my incline here, got my object. So let's just draw a net force, and then we'll draw a component next. And with the net force, I know that I have Fg coming straight down. I've got Fn perpendicular to the surface. I've then got a situation where this object is being pushed up. So I know I've got an applied force that's going up the hill, but at the exact same time, I've got a natural force that's being brought down by gravity. And because I'm pushing it up, my frictional force now is down the hill. It's there to assist gravity. Because if you're pushing something up a hill, right, then the goal is to get it up the hill. The only thing that's going to stop it would be friction from the surface, if the surface even has friction. If the surface doesn't have friction, then you'd only have three forces acting on that object. So when I draw the component diagram then, right, in this component diagram, I've got my force of my normal. Directly below that, I've got mg cos theta. Going down this way, I've got mg sine theta. And then going up the incline, because I'm pushing it up the incline, I've got a force applied. So that would be if you just push something up, something frictionless. But if I have friction, then I must understand, because I'm going up the incline, friction would want to bring the object down the incline. So my frictional force actually assists my mg sine theta. So that's why I say, like, the component free body diagrams are a little bit more useful, or they provide us with more information, so that when I'm doing F net, for example, I know it's going to be my force applied minus my force of friction minus mg sine theta. Right, in the last situation that we have here is when we have masses that are hanging in equilibrium. So when we have masses, what we need to understand also is when I draw my setup, please understand that these lines are parallel to each other. So if I know, for example, this angle, according to alternate angles, then I know that angle. So we can apply grade 9 rules for geometry for my angles. With these situations, I've got my object here in the middle. Going down is going to be mg. I'm going to end up here with ft 2. On the other side, ft1. And I know that on this basis here, I have two angles, let's say 45 degrees and 30 degrees. Notice here, no normal force, because it's hanging from that spot. Right, so those are your free body diagrams, all the different kinds, all the different scenarios. And then you get into the next, have a look at the next lesson.